Okay, good evening, everyone. We will start the session now. I'll let others join. If somebody is joined, let them join in between. And if somebody messages, ask them to message in the WhatsApp. You can reply to the chat because I cannot see the chat once I switch to the screen. They can ask, they can put the message in the chat WhatsApp. Okay, so we have one more participant here. Okay, so in the last session, we had discussed about the diodes and the transistors and the application of these diodes and transistors. So we'll have a quick revision now about the transistor. So diode is nothing but there are two types of material, that is p-type material and n-type material. If we combine these two materials, then we will get a p-n junction device. And in between, there is some junction is formed, so that is called as p-n junction. And diode to work as a forward bias, means a diode to work as a switch, we should connect a positive voltage to that, to the P side, and a negative voltage to the N side, so that it works as a proper diode. If we reverse the voltage, then what happens is that the diode will be in an off state. So this is a reverse bias condition. Here what happens is that we connected the reverse voltage, that is positive to the N side, that is to the cathode, and the negative to the anode side, so that will make the diode as reverse bias. And the transistor is nothing but it's a three-layer device where we have, say, like p-type of material is sandwiched between the two n-type of materials here, so that is why it is called as NPN transistor. So transistor short form, it is written as T/R. It represents the transistor, so it is a transistor. The full form is transistor. Short form is written as T/R. This is NPN transistor, and the other one was PNP transistor. So I will write both here. So let us write quickly. So normally the middle region will be very narrow. This is PNP. This is emitter terminal. This is base and collector. Okay, somebody is waiting to join. Okay. Okay. All right. Okay, those who have joined just now, we are just started the session and we are doing the revision of the previous session. So in the previous session, we discussed about the diodes and transistor and its applications. So transistor is nothing but it is a three-layer device. So we have three layers, that is P and P here. So here the N region is sandwiched between the two p-type materials. Okay, you can just think of a burger. So where in a burger in middle we have some kind of what do you say, the patty in between the two breads. So these are the two breads, that is P and P. It is of same type, and this is a patty in between. So it's something like that you can think of. So this is a PNP transistor, and it has a three terminals, that is emitter, base, and collector. Likewise, there is another type of transistor. If P type of material is sandwiched between two N type of material, then it is called as NPN transistor. This is NPN. This is PNP transistor. And this will also have three terminals, that is emitter, base, and collector. So basically collector means it collects the charges. That is the meaning of it. So base will control the flow of current, and emitter is where the current is entering or leaving. So likewise, the symbol of this PNP transistor is something like this. This is the transistor symbol. This arrow mark represents whether it is PNP or NPN, and also it indicates which is the emitter terminal, base, and collector. So this is emitter, base, collector, and this is PNP transistor. Okay, this arrow mark is towards this this line here, so it indicates it's a PNP transistor. If it is NPN transistor, then the symbol is similar, but only thing is that the direction is in the opposite direction. So this outward arrow mark indicates this is a NPN transistor, and this terminal wherever this arrow mark is there, so that is emitter, this is base, and this is collector. So hope this is clear to you all. Now I just want to discuss few more things related to this transistor. So transistor can be connected in three fashions. So first is common base, okay. So first is the common base, second is common emitter, and third is common collector. What does this mean? Common base, common emitter, common collector. I'll just write a simple circuit. This is P. This is PNP. Okay. This is P. This is N. This is P. This is emitter terminal. This is the base terminal, and this is collector terminal. Okay. This is some resistor, say R1, and this is another resistor R2. So let us call this as VEE, and let us call this voltage as VCC. So what is happening here is that if you write this in terms of the construction, this is P and this is N. So what is the voltage that we have applied? So positive voltage is that we have applied between the emitter and base. So what will happen? The current will flow from P to N. And as you see this, the positive voltage, this is P type. So what happens? That will make, it is just like you can think of a diode, which will make the junction as a forward bias, and the current will flow from emitter to base. And now, if you think of this section, the collector section, so collector is reverse biased. Reverse biased in the sense we have applied the negative potential. You see, this is a negative potential here, but it is a P type. So what happens? The majority carriers are whole, so this will be attracted towards this potential. So this will make this and this as a reverse pass. That is the collector and base as a reverse pass. So this is called as CB junction. This is called as EB junction. So this will be forward biased, forward, and this will be reverse bias. So when it is a reverse bias, then what happens? Whatever the current has moved to base, that will move to the collector due to the reverse saturation current. And now whatever the charges that is at the emitter, it has now reached the collector. Now in this case, we can write the collector current IC is equal to alpha times the input current, that is IE. Normally this value of alpha will be equal to 1. So it means if I give, if the input current is say 1 milliampere, okay, let me write here. So IC is equal to alpha is 1 ideally into 1 milliampere if it is the input current, then what is the output that I get? Output also I will get it as 1 milliampere. Is there any change in the output? There is no change in the output. So output remains to be same. Why? Because the value of alpha is 1. We can also write the alpha as the ratio of output current to the ratio of input current. This is the formula of this. So in common emitter configuration, sorry, in a common base configuration, because base is common between the input and output, that is why it is called as common base configuration. Common base configuration, the amplification factor is represented as alpha. So alpha is what? It is amplification factor. It is an amplification factor. Okay. So ideally its value is 1, but practically its value is less than 1. Less than 1 means it will be 0.995, 0.95, something like this. It will be there. This is common base configuration. Let me write the circuit for common emitter configuration. So here this is common emitter configuration. This PNP. Now if you see, this is P terminal, this is N, this is P. So again, N to negative, P to positive. It means it is again forward biased. And if you see here, N we are connected negative, and here we have connected positive. So it means basically this is grounded. This is a ground point. So this is reverse bias. So now what happens is that now the emitter terminal is common between the input and output. Now what is the input? Base is the input, output is collector, and common terminal is emitter. That is why it is called as common emitter configuration. Common emitter configuration. And in this case, the amplification factor is represented by beta. So beta is equal to, again, it's a ratio of output by input current. Output current is IC. Now the input current, since it is a base, since it is a base, we call it as the IB, and this is a collector current, we call it as IC. We call it as IC. Therefore, the beta is equal to IC by IB. And always the IB will be very, very small in terms of microamperes, whereas IC will be in terms of milliamperes. So obviously the value of beta is very large. The value of beta range from, say, somewhere around 50 to 400. As just a simple example here, if we take, if IC is equal to beta times IB, and if it is 1 microampere is the input current, and if the value of beta is equal to, say, 100, so what is that we will get? So 100 into 1 microampere, so output I'll get across 100 microamperes. So is the output is increased, or it remains to be same as the previous case? Okay. Okay. So somebody else was waiting to join. I think they have joined now. Okay. So now if you can see here, we have achieved the increase in the amount of output current by 100 times. So it means we have achieved the amplification. Amplification in the sense we have increased the input to 100 times, and we got the output as 100 times the input. So that is why in most of the circuits we will going to use the common emitter configuration rather than common base configuration. So common emitter configuration is most widely used in amplifier circuits. Why? Because if you want to achieve amplification, then we need to connect the transistor in common emitter configuration. It means the emitter terminal is common between input and output. So hope you understood this point. Now once you understood this, now let us move ahead with further topic here. So basically, before we apply any sinusoidal signal to this, we have to bias this transistor properly. So biasing means we will apply this, we'll put this in a circuit where it will give the proper voltages to its emitter, base and collector, so that it can fix its Q point. Some of you may know what is a Q point. So this is a normal circuit. So let us call this as R1, R2. This is RC. Okay. I think somebody is waiting to join. Then, yeah. Okay. So I think we can continue now. So I was telling you that before we apply any sinusoidal signal for amplification, so what is our ultimate purpose? Amplifier means. Amplifier means it is nothing. Assume this is a system or some circuit. I'll apply some input. I'll apply a small signal, and I want an output which is of higher in magnitude. It means the signal is increased in its voltage level and current level. So the magnitude, we call it as a magnitude. So magnitude is increased. So what is this system? So that system is nothing but this circuit. Okay. So whatever we have written here, this is this circuit, what I am talking about. Okay. So how do we achieve this? To achieve this, we need to use the transistor. Okay. And the transistor need to be connected with a proper resistor so that it can give a proper voltages across this transistor. There is something called DC biasing. I will not go in much detail. I'll just give you a little bit of information about this DC biasing. Well, I'm not sure whether you will understand this. Most of you can with technical background. Well, this is called as output characteristic graph. So output voltage is VC and the output current is IC. So we will get something graph like this. This is for different input currents. So here the input current is IB. This is IB is equal to say 10 microfarad or 1 microfarad. Let us take it as 1 micro rather than 10 micro is very large. So this is 1 micro. This is for IB is equal to 2 micro and so on. Okay, so we can split this region into 3 parts, something like this. So this region is active region. So if we draw a straight line here, wherever this line is intersecting, this is called Q point. If you draw a straight line here on this, a slope, a line on this output characteristic graph, wherever this point is intersecting, we call it as Q point. This is Q1, this is Q2, this is Q3. So I have to select which Q point the transistor should be, whether it should be at Q1 or it should be here Q2 or at third point. So to decide that, we have to apply the proper voltage across its emitter. Okay. So that is called as a DC biasing. And this is a simple voltage divider circuit. Kindly remember this because we are going to discuss this again, voltage divider circuit, further when we talk about the amplifiers. So this is a simple amplifier circuit. So here we will be applying our AC signal. So this might be VI. And here I will be connecting the DC voltage, that we call it as VCC or anything. It might be plus 12 volts or something. It's a DC voltage. And this is the AC signal where I'm applying the signal. This is the AC signal, this one, which I'm talking about. And then I'll get an output across the collector. This is a collector point because this is emitter, this is base and collector. These are the capacitors. So let us call this as CC1. This is CC2, coupling capacitors. Here I'll get this amplified signal. Okay, so this is a simple amplifier circuit. And we have to choose a proper resistance values of all these R1, R2, RC and so on. And we can also add one more resistor here across emitter, that is bypass resistor. So this is about an amplifier. Now let us talk about an oscillator. What is an oscillator? In most of the electronic circuits, we need the oscillations, or we need some pulses. It will be better to collect Gmail IDs of all who wish to attend and then include them in the list of invitees. Sure, sir. That I'll do it. Okay. I will do that. Okay. There is a suggestion by Lakshmi sir that since there is an issue, okay, we will do one thing. I'll collect the email IDs from all of you so that I can send the email and you can join immediately to the class without waiting to join or to wait or to take any permission to join. So that will be much, much better. So at the end of the session, I'll be requesting you all to share your email IDs. You can type your email IDs in the WhatsApp. I'll be taking that email ID, and the next time I'll straight away invite you through mail itself so that you can just click on the email and you can join the session. Is that fine?
Yes, sir.
Okay, okay, thank you. Sorry for all this trouble. So we'll continue our session. I'll take the email. Yeah, you can type in the WhatsApp. I'll collect it. Not a problem. Now or maybe after the session also, it is fine. Okay. So let us talk about oscillators. So what is an oscillator? All of you use watch, correct? So how does this watch runs to? For a digital watch, it needs a pulse. So it needs a pulse for the watch to run. So that means it needs some kind of waveform. Pulse is nothing but, again, it's a kind of a square wave, something like this, which keeps on varying from, say, plus positive voltage to negative voltage, or maybe some voltage to 0 volts, something like that. So like that, most of the electronic circuits need pulse or waveform or something like this. So how do we generate this? So that is generated with the help of circuits called as oscillator circuits. Even in the computer to run the computer, uh, most of you have the computers or laptops, and you might have seen that it says the processor is 2.4 gigahertz. So what is this gigahertz means? It means the speed at which it is operating. So again, if you see the hertz, it is frequency. So it means we need some kind of pulse which need to be given for these electronic devices to work. Not every electronic device. So which runs on the pulses, it needs a pulses. That is what I can say. Maybe your watch or processor, computers, similar to that, any other device which needs a waveforms or something like that. So all those things are generated by oscillators. So there are different types of oscillators. The simplest one is the LC oscillator, LC circuit, which generates oscillations. Then we have, say, Hartley oscillator. Then we have Colpitts. This will come in your examination. I'll tell you what will be the question. Colpitts oscillator. And the most stable one which you use in watch and most of the thing, it is the quartz oscillator. Quartz crystal, you might have heard it. So quartz is a material again. So we use that material to generate the oscillations in a circuit. So these are the basically 4 types of oscillators or circuits which we'll use to generate the oscillations, desired oscillations. For example, we may need some low frequency or we may need some high frequency. That again depends on the circuit. So we can tune to this circuit so that we can obtain the desired oscillations. Now let us see the basics of this, how these oscillations are generated. To understand this, let us take a simple circuit here. Let us take a simple circuit of capacitor. Capacitor can also be written like this. This is an electrolytic capacitor. Electrolytic capacitor has the polarity, or just to avoid confusion, let us take a ceramic capacitor which doesn't have the polarity. Now these two are connected in parallel. This is inductor and this is a capacitor. Let us assume that initially we have connected this to some voltage, some external potential voltage, say 10 volts. Call it as V potential. Now what happens initially? The current flows like this and the capacitor will be charged to its maximum value. So it means the capacitor will be charged like this to its maximum value. And once it reaches to its maximum value, then what do we do is that we will disconnect this supply voltage. Once we disconnect this supply voltage, what happens is that the capacitor is initially charged to its full. Now what happens? Initially, most of the current will flow through the capacitor because till the capacitor is charged, it will allow the current to flow because it's a DC current. Once it is charged, it will block the current. It will block the current. It will not allow any further current to flow. So that is why the response of the capacitor, if you see, it is suddenly rises and then it will decrease. This is the current across the capacitor. This is how we will get. Now once the capacitor is charged to its maximum, then what happens is that we have disconnected the power supply. So once we disconnect the power supply, now this circuit will act like an oscillator. Means it will generate the oscillations. How does it generate the oscillations? Let us see. Now what happens, since the capacitor is charged, the upper plate is positive and the lower plate is negative. Now it starts to discharge through the inductor. There is no other path. It cannot discharge through this because the circuit is open here. Okay, the circuit is open here. It cannot discharge through this way. So the only path which it has is to discharge through inductor. Now it has to discharge through the inductor like this. Just a minute. Now while discharging, what happens? The current flows from top to bottom. So when the current flows from top to bottom, we know that when a current passes through the inductor, it establishes a magnetic field around it. It will convert this current to magnetic field. And then the current flows in this direction. Then what happens is that, let us write the circuit again here. Now in this case, what happens? The current is flowing in this direction. Now the capacitor is slowly discharging and the capacitor starts charging in the opposite direction like this. Now this inductor is magnetized, means we know that the electromotive force has been generated around this inductance. We have seen this in the initial classes. It establishes a magnetic field. Now what happens is that it will give maybe in one particular direction. Now the current flows in this direction because the capacitor start discharging in this, and now it has reached to its maximum, means the capacitor is charged with the opposite polarity, means the bottom plate is charged with positive potential and the upper plate is charged with the negative potential. Now it will not allow any current to flow further. Now the current will stop flowing. Okay, then once again this process will continue. What happens is that now once it is completely charged in this fashion, now the current starts flowing in the opposite direction. Now we know that the inductor, if the current direction changes, then again the magnetic field around it will also going to be reverse. Now previously, if the magnetic field say in the clockwise direction, we may get something like this. Now it is in the anti-clockwise direction, we may get the direction across the oscillations like this. It means the electromotive force that we will get across the inductor is the opposite direction. And this process continues. And now when the current flows like this, the capacitor again charge with the upper plate as positive, lower plate as negative. And this process infinitely, ideally it's supposed to be infinitely repeat, but practically what happens is that this oscillations will be, what happens, go like this, like this, like this, and it will die at some point. This is called as damped oscillations. It's called as damped oscillation. Why is this damped oscillation? Because whenever the capacitor is fully charged and the current flows from one direction to another direction, at every point of time when it flows through the inductance, there is certain resistance which is there of the material, or reactance. There is a certain power loss which takes place. So every time when the direction changes, when the current direction changes, there is a loss in power, and that loss in power will make the capacitor to partially charge, and this is the oscillations that will generate across this inductance. Hope you understood how the oscillations are generated. This is a simple LC circuit. Initially, we charge the capacitor by connecting the external potential, and the capacitor was fully charged. Once the capacitor is fully charged, we have disconnected this supply, and now it acts like an voltage source. The capacitor acts like a voltage source. Now the current will flow through the inductor in a clockwise direction, and it set up an electric field around the inductance, and we get one type of oscillations. It might be a positive peak. And once the capacitor is charged with the opposite polarity, then again the current flows with the anti-clockwise direction, and then the direction across through the inductance is reversed, and it will give the negative peak of oscillations. This is with respect to time. Different time we have different peaks. Like this, the oscillations keep on continue. Ideally, it should go like this. Ideally, if we see, it should give equal magnitude. But what happens practically, the magnitude is reducing. Why? Because there is a loss of power. And at some stage, the output will be zero. It is not called as sustained oscillations. Okay. To get the sustained oscillations, we have to connect in a proper circuit. So how do we get the sustained oscillations? To get the sustained oscillations, let us use the amplifier circuit. Same amplifier circuit I am going to use what we have discussed before, this voltage divider circuit, and here I am connect this inductance and capacitance. So remember one thing, we can use the same amplifier circuit to amplify the signal or to generate the oscillations. Only difference is that the type of feedback that we will use. For example, if we take this is an amplifier, if this is the input, usually for oscillator there will not be any input, but just for understanding I'll write it here. This is the feedback. So we'll take the partial value of the output or partial signal from the output and fed back to the input. This is an summer. If this is positive and the feedback is negative, it means it is negative feedback. In most of the amplifier circuits, we use negative feedback. Then the circuit acts like an amplifier. Rather than calling this as amplifier, let me call it as, yeah, this is fine. If the feedback is also positive, both will get added up, and the type of output we'll get is increase in oscillations. So this is called as the positive feedback. And most of the oscillators use, not most, almost all the oscillator use positive feedback. And negative feedback is applied for amplifier circuit. Basically, we use the negative feedback in amplifier circuit to reduce the noise. If you use positive feedback, then noise level is increased. Anyway, now let us write this circuit and see how do we actually generate the oscillations. Let's use PNP transistor here. This is VC, sorry. Let's apply the negative VCC because it is PNP transistor and there's a coupling capacitor here. And now I'm going to add my this tank circuit. Across this. This is my inductance, this capacitance. You know how this circuit works. The capacitor will be initially charged. Assume that it's initially charged. So the current flow through the inductor in one direction until the opposite plate of the capacitor is charged with the positive, and then the current flow in the opposite direction. Likewise, this will continue clockwise, anti-clockwise, clockwise, anti-clockwise, and the oscillations are generated. But the problem was that the oscillations are not sustained, means the oscillations will die after some time. To obtain the sustained oscillations, we have to apply to the amplifier circuit. Now this is an amplifier circuit. Pause. This is R1, this is R2, which we have seen before. Now if you see, there is no potential that is applied here. So what happens in this case is the noise, we use actually the noise to amplify the signal here. So this is the circuit which we use. Now for this circuit, we will do a little modification. And to get the sustained oscillations, we need to have a feedback here. So what do we do is that we're going to replace this circuit by an inductor. Sorry, we replace this resistor by an inductor. And that inductor will place close to this L1 inductor. Let us see what will happen. This is the resistor R1, this is resistor R2, and this, sorry, this is short. So what did we do is that this resistor we have brought at this point here and replace that resistor by an inductor. Okay, then what happens is, so here this is connected through a coupling capacitor. This is grounded. So what happens is that whenever the capacitor is discharged, then what happens? The electromagnetic flux, that is the magnetic field is created, and that magnetic field is induced here. Okay. Sorry. So this will generate an oscillation. So that oscillations will be amplified and coupled back. The portion of it will be coupled back here. So it means whenever the inductor is, so this will, the magnetic field is coupled back to this L2 to L1, so that the energy loss can be compensated. And whenever the current flows in this direction, or maybe in the anti-clockwise direction or in clockwise direction, there is a certain loss of power, and that loss of power can be compensated by this feedback. You can say this as the feedback circuit, which is feeding back the output. So output means here is the output. So it is giving certain oscillations here like this, and that oscillation part of it is fed back through a mutual inductance here to this, so that the oscillations are sustained. So then what happens now? The oscillations are sustained, means it is not going to die. So we will get a continuous oscillations like this. Understood? So this is the feed. So here I have written one block diagram. If you see, the portion of output is fed back to the input. So that is a feedback circuit. So here the feedback is an inductor. So likewise, the feedback can be either a resistor, inductor, or it can be anything. We can feed the output, portion of output back to the input through any way. So like this, we are compensating and we're getting the sustained output across this point. So before we wind up this session, let us talk about a few more topics and then we will wind up the session. So whenever we talk about these oscillators, there is something called reactance we have to understand. So even in a resistor, if we say resistor has certain resistance, means it will resist the flow of current. That is why it is called as resistor. It has certain resistance. Likewise, this inductor and capacitor also has certain reactance. We call reactance because it opposes the this alternating current to flow. Certain resistance it creates, that is called as a reactance. So the formal definition is the opposition presented by either an inductance or capacitance to an alternating current is called reactance of the circuit. So what do you mean by reactance? The opposition is presented either by an inductor or capacitor to an alternating current. Alternating current means the sinusoidal. Alternating current is called reactance of the circuit. And the inductance, the inductive reactance, is represented by XL, and XL is nothing but it is 2 pi f into L. Now L is nothing but the inductance, F is the frequency, 2 pi is omega is represented as 2 pi f, so that is the omega, the frequency. So inductive reactance is represented by XL, capital X, capital L, and its formula is 2 pi fl. So it means the inductive reactance is straight away related to the value of inductor. It means it is linear. As the inductance value increases, if this is an inductance value, sorry, not inductance, yeah. Anyway, inductance is also fine, but our concern should be not inductance, our concern should be frequency. So if we take the graph here, if this is the frequency, if this is the reactance, this is inductive reactance graph, then as the frequency increases, then its reactance also increases like this. What about capacitive reactance? So capacitive reactance is represented as Xc, which is equal to 1 by 2 pi F into C. So C is the value of the capacitor, F is the frequency, and 2 pi is, well, right. Now, if you see in this case, Xc is inversely proportional to the frequency. It means as the frequency increases, the the capacitor reactance decreases. So it is opposite to the inductance. If this is the frequency, then what happens as the frequency increases, the inductive capacitance value decreases like this. So the unit of measurement of reactance is, again, it may come in the examination, that is, what is the unit of reactance? That is again ohms itself. Like for resistance, how we have the ohm, even the reactance is also represented in terms of ohms. And then we will talk one more final thing here, that is something called impedance. So impedance is the total amount of opposition faced by an alternating current in an AC circuit, consisting of resistive equivalent to the resistance in DC circuit. It might be an inductance or capacitance. So let us write the formal definition of impedance. So impedance is the total amount of opposition faced by an alternating current in an AC circuit consisting of resistance, equivalent to the resistance in DC circuit. So it is, the impedance is nothing but it is the overall opposition faced by an alternating circuit in an alternating current, opposition faced by an alternating current in an AC circuit, which consisting of resistive equivalent to resistance in DC circuit. So next we're going to talk about the tuned circuits. So we're going to talk about the series resonance and parallel resonance. So this we will continue in the next session. If you have any queries, you can ask. So today we could not discuss anything about the rules and regulations. So in the next session, probably tomorrow or day after tomorrow, so I'll try to finish off at the earliest. So there is a lot of gap in the sessions. So we'll try to take the continuous sessions and we'll try to finish off the portions and the syllabus. If you have any queries, you can ask. Otherwise, we'll wind up the session.